Welcome to session 7, which is a continuation of the combinational logics design. In designing logical circuits, a key requirement is to minimize the number of gates that you use. So this you can achieve through minimizing the functions. So in this session, we'll take a more detailed look at how to accomplish this feat. So you should learn how to draw timing diagrams, define static zeros and hazards. Given a switching function, realize it using two-level circuits, which is free of those statics or dynamic hazards. Design a multiple output NAND or NOR circuit using gates, and then design a minimal two-level multiple output AND or OR gates. The key things are the design of multi-level NAND gates and design of multi-level NOR gate. Those are the two key things that you want to take away from this session. Again, it's chapter 7 of your recommended test, Fundamentals of Logic Design. So, how do you go about this? You simplify the switching function to be realized. You design a multi-level circuit of AND and OR gates. The output gates must be an OR. AND gates outputs cannot be used as AND gate inputs. OR gate outputs cannot be used as OR gate inputs. So there's that thing. Number the levels starting the output gate as level 1. Replace all gates with NAND gates, leaving all interconnections between the gates unchanged. Leave the inputs to levels 2, 4, and 6 unchanged, and then you invert any literals which may appear at levels 1, 3, and 5. So it's sort of an alternating thing that you do. So if you look at that, your level 5, level 4, level 3, 2, and 1, right? And then you invert the outputs here, so you change that from an OR to what? An AND. You invert the literals that go into it. Then you put you invert the inputs there. Again, you change that to a NAND gate. Yeah. You put inverters at the end of that, and then you change that again. So if you follow the rules or the previous slides and then work through this, you see how this inversion is done. So how to convert from an AND OR gate to a NAND network. This is how it will be done. And you realize exactly the same function. You could also realize this using alternative gate symbols. So, well, you have A here giving you what? A not A, or an A not here giving a not A. Right. So you can have that where you have not A, not B into an OR gate. Now, which if you OR that, yeah, that becomes what? Because really that is what? Not A or a not B, and then you not that gives you A and B. Again, you can work through this. This gives you an OR gate, this gives you a NAND gate, and gives you a NOR gate. This, again, you can verify this for yourselves by looking carefully at what the law says. You can have the NAND gates as well, right? So this is a NAND gate network. So you have an A, not B, right? So the function Z is represented using just simply NAND gates. And then you can represent this again in an alternate form, right? So you leave this unchanged. That's so the first one and the fourth one are sort of unchanged, only that you see that the inverters, they are gone. Yeah. So this is an equivalent AND OR gate. So you got an AND OR gate. So this one here has been changed to an OR gate. That one too has been changed to an OR gate, and the NAND gate here has been changed into what? An OR, two OR gates there for you. And it will realize the same function. So what you are seeing is that any of these networks could have been represented by the NAND gates. So as an example, design circuits with 4 inputs and 3 outputs, which will realize the following functions, right? F1, F2, F3, and those are the terms that need to be realized. I'm sure you should be able to write out the functions of the circuits for this as they are. So for the F1, when you put them on a gate, on a table, on the Kano map, this is what you get, right? So you can then write out the functions for each one of them. And remember that you have this and then that. So 2 inputs. So this is what you get, right? And then for the F2, you have this and then you have that, right? Again, two level, which you can verify this quite easily for yourselves, knowing that these are the ones that you need to have in the table. And then finally, F3, you have this and then that, which gives you this function. Right. You can then combine all of this, combine all of that into one simple circuit. So this one gives you F1, F2, and F3. You can verify this for yourselves, right? See how all of these are combined into one circuit. Now, 7-segment displays are standard things that you see. Why are they called 7 segments? Because it actually has 7 segments. We use them for display purposes in digital, in clocks, and so on. So here you have a circuit here that you need to design to what? Display this, right? And this is part of your assignment that you need to do. So what you want to be able to do is that given some inputs here, you can display the number that you need, right? So these are segments. You can think of them as light segments, numbered, let's say 1, 2, 3, 4, 5, 6, and 7, right? And the idea is that this circuit you design here should what? Display the desired number that you require, right? And that is your assignment that you need to complete. So I'm not going to dwell on it for too long, but I'll give you the necessary lesson that you need. Right. We can use the binary coded decimal for that, okay? Now, if you look, the numbers or the digits that we need to represent are 0 through to 9. That's what we can represent using the 7 segments, right? Now, you have 0, 0, 0. You can say, let's represent 0 with that. When all the 4 inputs are 0, then the output should be 0. Then 0, 0, 1 to represent a 1, 0, 0, 1, 0 to represent a 2, and so on. Up to your 9, the 9 digits that you can display, which is 9, which is 1, 0, 0, 1. So, for example, to represent the number 5, it means that you need the segment A to be on, F to be on, G to be on, and C to be on, and D to be on. Now, if I needed the digit 3 to be displayed, then you can easily think about those segments which should be on. It means A must be on, B must be on, G must be on, C on, D on, with only F and E being off. That will give me a 3. If you look at that, then you see that for each digit, the segments that need to be displayed are indicated on this section. So, for example, if you needed 1 to be displayed, it means you need the segment B and C only to be on, right? So that's the first thing you need to do, is to identify all the segments that need to be on when you need a certain digit to be displayed. you can do a table, right? This will help with your assignment that you are going to do, because this is part of your assignment. You can do a table. You have your inputs and then the outputs, right? The outputs are all the 7 segments, yeah, that you need. So the question then is, for example, if you need the digit 1, yeah, or the decimal digit 0, right? The inputs are 0, 0, 0, and 0. What are the outputs? Which digits or segments need to be displayed, right? So you put 1 under those segments that need to be displayed. So for example, to get a 0, you need A, B, C, D, E, and F to be displayed, to be on, right? So you put a 1 under all those columns. So that you do that for all of them. And once you've done that, you then minimize. Each of these will go into a separate K-map, which you then minimize, and then you get a circuit for. So this is for the segment A. You can write the same for segment B and segment C and so on, right? So now recall that we said something about I don't care or don't care positions, because really these positions here, you really don't care what is there because you are not using them. So you can put 1s there to help you to obtain minimal forms if you so desire. So we put X's there because we really don't care, we are not using them. And when the need arises, we can put 1s in those places. So as an example, you could decide to put 1 here, 2 1s here, and then you can minimize that, right? Or you can actually put 1s all here, and then it will help you to minimize the whole of that. So it's something you need to consider. So segment A, right? So you see, like I was saying, you can put 1s, all of them, and then you can minimize the whole of this, which will result in just W there, right? So we can write the functions for each of the segments, all the ones that you are minimizing. So you had 1s in these corners, and there's an X there, so you can actually minimize that. And then for this one here, you can actually minimize it using these X's. And then, of course, you see this 1, 2 here, these 2, you can also group all of those together, right? So this is something for you to think carefully about. You can put all the terms together and then get your F function for just an A segment. So for your A segment, this is what you get. And then you have to do this for your B segment, your C segment, your D segment, for all the segments. And once you've done that, you are good to go. So you have to do that for the A segment, the B segment, C segment, D segment, E segment, and the F segment. Yeah. So each output column will be in 1 circuit. Each output column will be what? In 1 circuit. So you do this. So you attempt to complete this for the B segment, and then that is it. So your task is to complete the 7-segment design for all the rest of them. Your tutor would help you with the rest of it if you need any help. But this is a task you must complete. Thank you.